Okay, the next section is 2.2, power functions, and we'll do some application as well. We'll learn about power functions and variation, monomial functions and their graphs, graphs of power functions. We'll do some application because this can be used in geometry, chemistry, and physics. Okay, so a power function is this right here, y equals k times x to the a. So basically what we had before, we had polynomial functions that we just learned about, like for example, a real simple one, a quadratic, right? Well, we talked about polynomial functions have to have positive integers here, but we did not talk about what would happen if we had like a fractional exponent instead of an integer there. That's not a polynomial. This is not a polynomial. We're going to call that a power function now. So now, basically, our exponent can be any number we want. It doesn't have to be just a whole number. All right? It can be a negative number. It can be a fraction. Any real number. Okay, so here's an example then. It says state the power of the constant of variation. So keep in mind that these power functions have this form. F of x equals k x to the a. So k is the coefficient, which in this case is 1. I'm going to rewrite this right here as x to the 1/4. I'll write it as 1 times x to the 1/4. So you can see that k is 1 and a is 1/4. So the power is 1/4, which is the fourth root. And the constant of variation, k, is 1. Now, if you do go to graph this, it's going to look something like this right here. Let's try another example then. It says describe how to obtain the graph of this function from the graph of this one, the same power of n. So same power of n would be, that's a 3, it's a little hard to see. But it's basically saying compare 3x to the third to x to the third. And how are they different? Okay, so the 3x to the third then is going to be a vertical shift. That's on our formula sheet. On the formula sheet, I'd say if you divide this by both sides, and y divided by a number bigger than 1 is a vertical stretch. So our regular cubic function looks like this. A vertical stretch then would just stretch it more vertically like that. Okay, so the book talks about what happens when you have, like for example, in the power function f of x equals k x to the a. What happens if this exponent right here is less than 0? If it's less than 0, like say -1, then, and you can rationalize all